Assalamualaikum warahmatullahi wabarakatuh. I am Muhammad Azri Zamir Rasid from University Malaysia Pahang, and on behalf of our team, I'll be presenting our paper entitled Evaluation of DC Motor Temperature Response Characterization Method under Different Sampling Times. So electrical motors are being employed in many industries, and heat dissipation is basically one of the major issue that we are facing and need to be resolved in the utilization of electric machines. So because in order to improve efficiency and keep the efficiency very high, we need to evacuate the heat properly from the internal of the machines to the ambient air. So thermal studies of electrical machines is a large area in the studies of electric motors and generators. So modeling, simulation, and assessment and diagnostic have been done for various reasons. For example, modeling uh, were done extensively to evaluate extreme condition where we don't want to create too much prototype that would be led into destructive tests to reduce cost of development. Modeling can also be done to basically to be used for parametric optimization for the same reason, to not develop too many prototypes and involving cost in evaluating the prototypes. So modeling are very important in this area as well of thermal studies. And then, of course, there is utilization of thermal assessment as potential method for fault diagnostic and identification. And this method is, of course, a very promising method, and a method that's been employed for quite a long time with a certain limitation, of course. But it is quite an interesting method in terms of cost when compared to more usual methods that are being employed, such as current evaluation, current measurement, MCASA, and vibroacoustic methods. So what is the problematic that we are facing that we try to solve in the study or evaluation of temperature in electric motors? So the first thing is that the evaluation of temperature in electric motors nowadays are mostly done in steady state temperature. This is for the reason that the utilization of machines are mostly in this kind of cycle where it is operates constantly at a constant load and constant speed. This is true for the utilization for example, for large industries in utilization it as pumps and ventilators. But the problem is that so this is an example where we have a handheld tool, right? We measure the temperature during operation, we read the steady state temperature, but it is not sufficient anymore because we use motors and more and more transient cycles, for example, robotic and automotive. So we can see here on the right is basically a figure of the cycle of operation that have to be executed by an electric machine in an electric vehicle. So it's very dynamic. So we need to evaluate the temperature, not just the steady state temperature, but also the transient state temperature. So a complete thermal characterization of motor need both the measurement of steady state temperature, of course, but we need to be able also to look to characterize the machine on its transient temperature rise. So it means that we need to not just measure the steady state temperature, but also indicate at which time do we reach that steady state temperature, right? So in what we call by temperature response is basically the temperature, the rise of the temperature that includes the transient phase and steady state phase as we inject in a certain amount of losses, right? So the temperature response, of course, depending on the type of the machines, because different machine will have different characteristic of thermal conductivity, specific heat, geometry and dimension, and of course density as well. So usually another problematic we're facing is that usually this measurement or this analysis of thermal characterization are done post measurement. It is done as a post treatment. So and then there's also the problem of the definition of steady state temperature can be inconsistent when we're dealing with transient state as well, because we know that depending on machines, the time that it needs to reach the steady state temperature can vary. Time that is too long mean people don't really know. When we look at transient state, we don't really know at which time it attains that steady state in reality. And then there's also the problem related to the fluctuations of temperature, basically due to the precision of the instrumentation. So the objective that we have in our studies is to create, the first one is to create an algorithm to identify the steady state temperature, and of course identify the time at which the steady state temperature is reached in the manner, in a consistent manner. It means we have to define certain parameters that let the algorithm to find out in the temperature response, where is the steady state temperature and when does it reach it. So in that algorithm, what we're going to do is, second objective, we are going to evaluate the influence of these two parameters in the algorithm, which we call the time interval delta t and temperature resolution delta temp. The influence of both definition of these parameters on the precision of the steady state temperature that we found. So as scope, we basically the algorithm will be written in MATLAB script, and the evaluation will be done using a temperature response that we get from the measurement on a small brush DC motor. So this is basically the test bench on which we install our small brush DC motor of 250 watts. It has been instrumented with thermocouple type K on various components, and then it is basically operated at constant speed at constant load. So we have an encoder to ensure the constant speed. We have a load attached to it, and we put a constant load, and then the temperature from the thermocouple are being measured and stored and monitored on our host PC. So in terms of the algorithm, I'll explain briefly. We'll go through the algorithm. It consists of three main phases. So the first phase is basically pre-processing the data. It means that we'll read the data, and then we'll define the intervals that I've mentioned just now that characterize the algorithm, define the time interval and temperature resolution. And then the second phase will be a loop that consists of running through the temperature response and try to find basically the steady state temperature using the definition of time intervals and temperature resolution. And then finally, once we get the steady state temperature, we will table it down following the two parameters. So the two parameters that we're studying is temperature resolution and time intervals. We will table down all the steady state temperature and the time at which the steady state temperature is reached. So in results and analysis, what we have found out is basically the steady state temperature TSS deduced is lower. So if we're looking at this graph, the steady state temperature that we deduce from the algorithm will become lower if delta temperature, so delta temperature is this axis over here, the axis X, if delta temperature increase. So as the delta temperature increase, we will find a lower temperature steady state temperature. And on the other side, in terms of the time interval, as the time interval increase, we will find a larger or higher steady state temperature. We'll deduce a higher steady state temperature, right? So the same goes for the times. Therefore, the time will be lower here, and the time will be longer to identify the steady state temperature over here in this axis. But we can remark also one important thing. I'm sorry, it's behind my video over here. That there are several points that cannot where we cannot manage. We didn't manage to find the steady state temperature. It is when we have the delta time or time intervals to a large time intervals and a very small temperature resolution. So why does this happen? This happen due to the fluctuations of temperature that will never settle. So we set over here is basically the point where the temperature resolution is very small. We will never reach a small enough temperature intervals, temperature range, because there is always a fluctuations due to the precision of the thermocouple, right? So we also basically computed the precision. So the precision is basically the precision of the temperature steady states found compared to a reference steady state. Of course, it's the inverse of the graph that we found previously. When the time is the time to find the steady state temperature is shorter, basically the error that we found is larger. Here we listed down the pair of DT and DTEM that give a largest error, and also that there's a pair that give the smallest error. And then another thing that would be interesting to do is that if you can accept to analyze the temperature response for just a percentage of the actual steady state, we can basically have a potential time reduction in diagnosis. What does it mean is that instead of measuring up to the 100% of steady state temperature, why don't we just measure up to only a certain percentage, so that we basically save times in measurement. But in order to do so, of course, there is a limit. There is a certain definition of DT and DTemp, delta T and delta temp, that need to be done. And this two graph indicates the influence of DT, delta time and delta temperature that need to be used in order to get the optimum diagnosis time reduction. So that's all. So in conclusion, an algorithm have been developed. The algorithm was tested on the temperature response of a brush DC motor. To attain the highest precision possible, we need DT time intervals, large time intervals, and the smallest possible temperature resolution. But of course, it is limited by certain precision due to fluctuations. I mean, limited by certain fluctuations due to precision of the instrumentation. And inversely, what we can do is that we can also use the fact that measuring only a percentage of steady state temperature, if we have a reference, can be an interesting way to reduce diagnosis time. So for further information, you can read the paper, and you may visit us at our website. So thank you very much.